Okay, so lecture 13, and today we are going to look at diagonalization. So the question we can ask is, what matrices in a complex vector space are diagonalizable? That is, for what matrices in the complex vector space, CVS complex vector space, there exists a basis in which the matrix is diagonal. So this is a central question, and well, the answer is most. We'll elaborate on that. The idea is that first of all, recall. I'll just give you the logical flow, and then you can follow this, fill up the steps yourself. So first, recall that an operator or a linear transformation operator is when it's going from the same vector space from V to V. An operator expressed in the basis of its eigenvectors is diagonal. Now, well, that's mm, kind of easy. We already saw that this condition and this an if and only if condition. If it's diagonal, then its basis is the eigenvectors, and if the basis is the eigenvectors, it's diagonal. And this comes from the notion of invariant subspaces. So let's say I have a linear transformation, and if there exists invariant subspaces such that the vector space is a direct sum of invariant subspaces, vector space under this linear transformation is a direct sum, can be decomposed as a direct sum uh, of invariant subspaces. Well, then the matrix of the linear transformation can be expressed as some block diagonal form. And in what basis? So if I just write down a basis of the ordered eigenvectors of these bases, let's say v1, v2 are the eigenvectors till some vr. So in this particular basis, I'll have the matrix which can be written in this form, and that matrix you can check by inspection also that that's going to preserve the uh, invariance of the subspaces. And we can extend this when the invariant subspaces are really one dimensional, then I have a diagonal matrix when the invariant subspaces are one dimensional. And not only that, yeah, so, and the basis for this is the eigenvectors. You can check that. So essentially, any matrix is a diagonal matrix in the basis of its eigenvectors. So essentially, what do we have? We have, if we want to find the condition that the matrix is a diagonal matrix in some basis, it boils down to the condition that you know, the operator, I'm going to use operator and matrix interchangeably, it doesn't matter, uh, should have a basis of eigenvectors. And what is the condition for that? Well, the condition for that is that the characteristic polynomial, the characteristic polynomial has n distinct roots. So we have what happens then? So if it has n distinct roots, one can show that this implies that one has linearly independent eigenvectors. How many? N. N is the number of eigenvectors. So if I have an n-dimensional vector space with n linearly independent eigenvectors, well, they form a basis. So then I'm done. That I have a basis of eigenvectors, and as long as I have a basis for eigenvectors, the operator of the matrix is diagonal. So how do we prove that if the characteristic polynomial has n distinct roots, then it does have n linearly independent eigenvectors? Well, let's see. So we can prove it by induction. So let's say we have this result at hand. Our typical condition for linear independence. These are the vectors we need to see if they are linearly independent or not. So I apply the transformation. I apply the linear transformation T, and that gives me, since these guys were the eigenvectors, let's say that gives me C1 is the eigenvalue. So I'm applying T to this guy. That yields me A2, C2, V2, AN, CN, VN equals to 0. So what do? I take the first equation, so this is my first equation. I multiply this guy by C of n, and I subtract it by this guy. So what do I get? I get this guy minus this guy. which gives me, wait a minute, did I screw up somewhere? Sorry, I think I copy pasted the wrong thing. Yeah, so I just subtract this guy. Okay, so what do I get? I get essentially A1 C1 minus Cn plus V1 plus A2 C2 minus Cn V2 An minus 1 Cn minus 1 minus Cn Vn minus 1 equals to 0. So what does that mean? So if I apply the induction on n minus 1, I assume that these guys are linearly independent. So this implies, and I know that the eigenvalues are distinct. The roots of the characteristic polynomial, that the eigenvalues are distinct. So I get a1 equals to a2, an minus 1 equals to 0. So I'm left with a trivial relation that I have got this guy an cn is equals to 0, which implies an is also equals to 0. So the expression I was examining, this has all the coefficients a1, a2 till an 0. So these vectors are indeed linearly independent. So that shows that the eigenvectors with distinct eigenvalues are linearly independent, and there are n of them, so they form a basis. Eigenvectors form a basis as they are linearly independent, and n of them, which implies that I have found the basis in which the matrix or the operator is diagonal. So mind you, this is a sufficient condition. This is not a necessary condition, but at least we have got a sufficient condition. And our argument was hinged upon a complex vector space, but you can make a similar argument for any particular field, so to speak. So that was the essential part of it. So I'll just write it down as a theorem. And the theorem says, let T be a linear operator on a vector space V of dimension n over a field f. Assume that its characteristic polynomial has assume that its characteristic polynomial has n distinct roots and distinct roots in f. Then there is a basis. Then there is a basis for V with respect to which the matrix of T is diagonal. Essentially, that's what the idea is. So there's a corollary. The corollary says that A prime equals to sum. This was the original matrix, P minus P prime. These are invertible matrices. Is diagonal, because any change of basis, starting from some basis over here and getting the basis to be the eigenvectors, involves this sort of a transformation, hitting it with P and P inverse. We saw that. So that is it. And what is this P? Well, this P has to be certainly related to the eigenvectors, because that was our basis change, and that is actually given by, remember, I had a new basis which was given by some matrix P. Sorry, this was, yeah, and this was the old basis, which was the standard basis. So P is nothing but, so standard basis is just the identity matrix. So I get P as B inverse. So the B inverse, what was it? This was just your eigenvectors expressed as column vectors. Inverse of that matrix gives me this matrix P. So the eigenvectors, once I know the eigenvectors, I can express this as a change of basis, and this matrix is going to be a diagonal matrix. Okay, so one last thing about this chapter was, this section was the proposition, kind of related to what we have been doing, but we just mention it. And it is that to say that let T be a linear operator on a finite dimensional vector space let's say complex vector space V. Then there is a basis B of V such that the matrix A of the linear transformation is upper triangular. In other words, if I have an n by n matrix A, it is similar, that means it is similar to an upper triangular matrix. This is the matrix version of the same thing, because we know that any change of basis is these guys. So how do we sort of see this? Well, it's rather easy. So you can easily see that if I have, so essentially the observation is that the fundamental theorem of algebra states that any complex polynomial has a root. That means it has an eigenvalue, has at least one eigenvalue, which implies it has one eigenvector. Now, if I make that eigenvector the basis, my matrix can be written as that particular eigenvector. I'll just mention it first only. So that's my first vector of the ordered basis. And I have some matrix. So this is the form of the matrix, such that this A prime boils down to finding that particular eigenvector and using it as the basis over here. So I have this form of the matrix after the first sort of a transformation. So I can show this to be an upper triangular matrix to some sort of an induction. What I can do is that I can imagine that B is a matrix and n minus 1 cross n minus 1 matrix such that QB Q minus 1 is upper triangular. Now it boils down to proving in induction, mathematical induction, we show it for n minus 1, assume for n minus 1 and prove it for it. So what does it boil down to? So consider one particular matrix of the form n by n matrix. Let's Q1 be an n by n matrix, which will do the job of this particular form. This has a form 1 0 0 0 0 whatever 0 0 0 something, and this is my matrix Q, which was related to this guy. So Q. So now what's the action of Q1? So consider some matrix applied Q1, sorry, Q1P inverse. So what does it give me? This gives me Q1 PA P inverse Q1 inverse. That gives me Q1 A inverse Q1 minus 1. Six, 7. So what do I get? This matrix, if Q1 is this guy, you can check it. You hit it with A prime. A prime was of this particular form, and this will have the desired form. This will have the form of C1 0 0 0 0 something, and this would be QB Q inverse, because hitting Q1 already had some Q in it. So I have this Q1, I put it in A prime and I put it as Q1 minus 1. That is going to have the desired effect on this guy to be having this particular form. And through my induction hypothesis, I already know that this is an upper triangular matrix. So the combination is, that is a has form of an upper triangular matrix. So this is one way to prove our assertion out here, and that is it. So that was about diagonalization. Uh, what is the advantage of diagonalization? Why do I make matrices diagonal? Well, the idea is that it is easier to take power. So let's say I need to take a power of k of some matrix. It is much easier to, I know if the matrix is diagonal, A prime, taking powers is rather easy. A prime k would be just exponentiating the a diagonal matrix, only the diagonal entries. So this can be written as P inverse A inverse, the diagonal one, diagonal matrix. This is just a change of basis to the power of k. Now, what is this? This is just P inverse A prime P k times P inverse A prime P, P inverse A prime P, so on and so forth. These guys form identity, they cancel. So I'm left with P inverse A prime to the power of k P. So this is computationally rather easy to calculate since it's a diagonal matrix. So this helps me, instead of multiplying a complicated matrix k times, I can just consider this form exponentiating to the diagonal matrix and then putting the change of basis. So this was all about diagonalization we studied. We'll be doing something very interesting in the next lecture, very connected to diagonalization itself. Thank you.